Hi everyone, good afternoon. My name is Prateek Maheshwari and I work at LinkedIn on online databases. So at LinkedIn, we intend to run TiDB as a managed service offering at a very large scale. But before we can do that, we need to learn about the system's scaling, operability, resiliency characteristics, everything that Sunny just talked about. And in this talk, I'll be sharing our experiences and experiments with running that so far. But first, what does LinkedIn Scale mean? So as you guys are aware, LinkedIn is a global professional network. Our economic graph is a digital representation of the global economy, and that consists of over 1 billion members, 67 million companies, 41,000 skills, and 133,000 schools. In terms of data and systems, this means over 2.5 million site traffic QPS, over 45 trillion Kafka messages produced and sent within the data centers, hundreds of petabytes of online data, and exabytes of data in the data lakes. And in terms of hardware footprint, we are operating out of multiple geo-distributed data centers with an active setup, which overall add up to hundreds of thousands of servers. For a scalable system, operational considerations are equally or even more important. All of our infra systems have to serve a large variety of use cases, have very strict availability requirements, 4 nines or higher, with no scheduled downtime, no planned maintenance downtime, have to be multi-tenant for efficiency and have to have predictable performance for all tenants, and need to be resilient to constant changes in the operating environment, hardware changes, upgrades, software upgrades, faults, everything. Our goal is to run TiDB as one such scalable system at LinkedIn. As a canonical example of what we're trying to use TiDB at LinkedIn for is a large-scale serving system. So such a system would host multiple large data sets, allow bulk loading large amounts of data into the system, and serve a variety of application queries. We need large clusters to serve cross-data set joins and indexes and lookups. We're talking about several million QPS and several petabytes of data in a single cluster. And we need features like bulk load, cross-data center replication, backups, restores, maintenance, everything, again, that Sunny just talked about to work at scale without affecting query latency for the live query systems. So let's talk about scalability first. At a high level, you guys might be aware, TiDB consists of a distributed SQL execution engine, also called TiDB, a strongly consistent KV store called TiKV, and a central coordinator called placement driver that has a couple of major responsibilities. In the current architecture, we expect TiDB and TiKV to be mostly horizontally scalable. We expect the placement driver to be the eventual bottleneck for scaling QPS and storage. So we want to establish the theoretical upper limits for PD scalability for a single cluster through micro benchmarks before we start. So let's discuss QPS scaling first. In TiDB, because it's a strongly consistent relational transactional system, every transaction is associated with a globally unique, monotonically increasing timestamp, which is fetched from the PD, which also serves as the timestamp oracle. And at a given time, there's a single PD responsible for serving all timestamp requests. And you can imagine this is obviously a bottleneck. So to find out the limits of a QPS that a single cluster could hypothetically do, we need to benchmark this API. Now, there's 2 components to the rate of TSO fetching. One is the number of gRPC requests from TiDB servers to the PD to fetch these timestamps, and another is the batch size of each TSO request, because each request can request multiple timestamps in one batch. Now, the degree of batching is workload dependent, depends on how many queries your TiDB servers are serving per second, and they can batch whatever requests come in within one round trip in the next request. So we want to actually benchmark the gRPC throughput because the other half is workload dependent. So we observed that the one thing to note there is somewhat counterintuitively, bigger and fewer TiDB servers is better for QPS scaling because they can batch TSO requests more effectively and prevent you from hitting the bottleneck, as opposed to smaller and very many TiDB servers. So in our experiments, we observed around 200K QPS for gRPC requests between TiDB to placement driver. And the bottleneck on the placement driver was lock contention for generating the timestamps. because it's a globally unique, monotonically increasing timestamp. So as you can see on the graph on the right, the request QPS from TiDB to PD for the TSOs increases up to 200K QPS and then saturates, and then the latency starts going up and the CPU utilization starts going up. The 200K is not, just to clarify, not the upper bound on how many QPS you can do. For example, if each TiDB server could batch 4 requests within each, 4 timestamps within each TSO request, you could get up to 1 million QPS, and that's very reasonable. That's pretty normal. So during our experiments, we found a few tunables that can improve the TSO throughput with various trade-offs. For example, running PDs on machines with faster single cores and more cores can help with the gRPC connection overhead management, and then help up to a point until the lock contention kicks in. There's a feature called PD follower proxy that distributes gRPC request handling over not just the leader PD, but also the follower PDs. This can reduce the load on the leader PD, like freeing it up to do other kind of requests it's responsible for, and also reduce tail latencies because of lower load overall. But the downside is there's now an extra hop between the followers and the leaders to fetch the timestamp because the leader is still the source of truth. So it may add a little bit extra latency at the benefit of giving you better tail latencies. Another feature is TSO batch max wait time. So like I mentioned, the degree of the 200K is the gRPC QPS limit, but the actual number of requests or timestamps you can generate depend on the batch size within each request. So you can force TiDB to add like a minimum batch wait time to batch up requests within that interval. Of course, this will give you better throughput for TSO, but will increase the latency for your overall requests because this adds a minimum wait time for each request. And at very high QPS, we've observed there's another configuration for how the timestamp on the PD is composed of 2 parts. One is the physical timestamp based on the physical clock, and one is the logical incrementing counter. So it's like a complex vector. The frequency of update of the physical part is tunable, and if that's too low, you can end up in a situation where at high QPS, you run out of the logical timestamps and then the request processing stalls. So you can fix that, you can tune that at the cost of higher CPU overhead for updating the physical timestamps up to the order of like 10% of CPU utilization. And in addition, in the newer versions, I think there's a new feature called TSO microservice coming, which separates the TSO handling functionality of the PD into a separate process, which gives us, again, better isolation and more headroom to process these TSOs. So it's still a singleton, but it's a separate singleton from the cluster management part of the PD. So that's for timestamps and queries. Again, timestamps is the bottleneck for the queries. The other aspect of scaling is data size in the cluster. And here too, we expect the PD to be the bottleneck eventually. So for context, in TiDB, TiKV stores and replicates data in fixed size chunks called regions. And the default region size is 100 MB, roughly 96 MB. The maximum number of regions in the cluster, and hence the total data size, is again bottlenecked by the PD. This is because for ensuring availability and load balancing within the cluster, the PD, every TiKV store in the cluster needs to heartbeat every single region it's a leader for to the PD at a fixed interval. The default is a minute, right? So the PD has to handle a lot of these heartbeat QPS as well. And again, it's a singleton, it's a single leader. For example, if the cluster has 100 TiKV stores and total 1 million regions, which is roughly, I think, 100 terabytes of data. Each store would be, but don't count on my math, just do the math yourself. Each store would be sending about 1,000 heartbeats per minute to the PD. In our experiments, we observed up to 10 million region heartbeats per minute. And again, the current bottleneck is some lock contention on the PD for updating the region metadata consistently. You can see in these experiments, the QPM, requests per minute, for these heartbeats go up to 10 million regions, and then the memory usage on the PD starts increasing. So if we sustain this load after 10 million QPS, it would eventually run out of memory and crash. So for the default setup of 100 MB region size, default heartbeat interval of 1 minute, this is roughly 1 petabyte of logical data, and then it can be replicated with whatever replica factor you configured in the cluster. Again, this is the theoretical upper limit. This can be further tuned with some trade-offs. For example, of course, increasing the region size above 100 MB would give you more data with the same number of regions, but that has some trade-offs. For example, it could create hotspots in the cluster because many queries are going to the same region. And it has implications for maintenance because now you have, if a host goes down, you have to move, let's say 1 GB chunks of data around to restore that host. There's another the other thing you can do is increase the heartbeat interval over the 1 minute, but of course, this gives you for the same QPS a larger number of regions and hence more data, but then you get lower reactivity to disruptions within the system because the PD doesn't realize until much later there's something wrong in the cluster. Another feature that's enabled in newer versions by default is called hibernating regions, and the idea is in a typical cluster, not all the regions are taking traffic at the same time. There's probably a long tail of inactive regions and then a short tail of very active regions. So it just reduces the heartbeat frequency for the regions that are not actively taking traffic. That works great, except the nuances, the percent of hibernating regions is workload and time dependent. It's possible because of traffic shifts or varying workloads, the percent could vary wildly. And they occasionally wake up, they periodically wake up every few minutes and then start heartbeating. So it's not a panacea. There's some work to be done there. There's other improvements. For example, like I mentioned, they wake up at the same time, so we can introduce jitter to the system. We can batch heartbeat requests from the store to the PD instead of making one request per region. And like I mentioned, there's a separate microservice coming, which will separate the TSO and the cluster management region heartbeat workloads on the PD, ensuring better tail latencies. Okay, so something interesting we found while benchmarking this stuff at very large scale. By very large scale, I mean we were benchmarking the PD performance with very high CPU core count, let's say 128 cores at very high QPS, the numbers you saw earlier, and with high connection counts, so lots of TiDB servers trying to connect to the PD. What we observed was because of how Golang, which is what the placement driver is written in, because how Golang's networking library uses epoll. It uses a single epoll instance for all threads. We see at this scale a very high system CPU usage with over 50% of the time being spent on spin locks within that epoll instance, which is just wasted CPU. And the workaround is just to reduce the number of threads within the Go process. And that gives you, for the same QPS, lower CPU utilization and better predictable tail latencies. This is a bug in how, or a issue with how Golang does its networking. Hopefully this will be fixed in future Go releases. But this is the kind of stuff you don't really figure out until you exercise the system at extreme scale. But turns out the benefits of doing this would be applicable even at lower scale. You just don't observe it as clearly. So that's for scaling QPS and storage in the cluster. In addition to scaling, we also need some operability features for adopting TiDB at LinkedIn. The first and probably the most important of this is async cross data center replication. So for context, LinkedIn operates in a multi-data center spread across the world in an active-active architecture, which means at any time, all of the data centers are taking user traffic and writing writes and serving writes. TiDB's synchronous replication across data centers would not work for us. It has too high latencies with the distribution we have. So we have to build a asynchronous cross-data center replication with last writer wins eventual consistency conflict resolution. The trade-offs, the benefits we get from this are better resiliency overall for the website and lower latency for each individual colo that the request is going to. But of course, the trade-offs are we have to give up on strong consistency offered by TiDB and settle for eventual consistency. And then we need some extra metadata for doing last writer wins conflict resolution. At a high level, the way this works is we use TiCDC change capture, which is available as part of TiDB, to write all changes in the local data center to the Kafka topic. And we have in each remote data center a Flink job that pulls from this Kafka topic and writes to the destination TiDB with some conflict resolution logic. We had a recent talk, if this is of interest to you guys, and we've heard plenty of interest in this kind of setup. There's a recent talk at the TiDB open house which goes into a lot more technical detail about this, so I'd highly recommend checking that out. So we did face some challenges while building and operating this at large scale, especially with TiCDC max throughput and reliability that we've been working through with help from PingCap over time. And another issue with this setup is that this design requires some user-visible metadata columns in each table to do the last writer wins conflict resolution. For example, the source data center, the timestamp of each write, the timestamp for resolution of each write, etc. These columns are user-visible, which means we now have to also provide a client that can wrap over the logic for updating the metadata correctly and also filtering delete tombstones on the read side, which is extra overhead for us to manage. So ideally, we would like to do this transparently from the users, as in they don't have to see all of this plumbing in the background, which would need features like hidden columns within TiDB and query rewriting to do this at write time and read time before the request reaches the user. Another operability feature we need for this serving system use case is fast bulk loads. So like I mentioned, this is a serving system. We have other source of truth data stores with large data sets, and we need to bulk load new data sources or update existing data sources with a new version because of schema changes or whatever else with a very high QPS without impacting the latency in the real cluster. Some of these data sets are quite large, tens of billions of rows. So we need to bound the amount of time this operation takes, right? It can take up to a day, that's fine, but it cannot take like over a week because that's too long to get to the latest data set for whatever reason. And we have to do this without impacting online traffic latencies. We tried several different approaches for this. The simplest one is SQL-based inserts. Either just bash them or do them one at a time. We achieved up to like 70 to 80K QPS with moderate latency increase on the live cluster. But that would take too long, like over a week for the larger data sets that we have. So that doesn't quite work for us. We also explored TiDB Lightning, which is a bulk load tool available out of the box with TiDB. It has two modes, logical mode and physical mode, to import the data. The logical mode has similar performance to the SQL inserts, both in terms of throughput and latency impact. So that's a no-go for us. And the physical import can achieve a much larger QPS, like we saw even up to 1 million QPS, but that's highly disruptive to online traffic. It's not really meant for running on a live cluster. It's really meant for like bootstrapping a new cluster. Even with throttling to get it to an acceptable throughput for our like serving time, to bulk load time target, we still see a very high 2 to 2.5 times latency impact, which would not be acceptable for us. So this is an open problem for us. We haven't solved this yet. We haven't found a good solution. If this is something you guys have already thought about or worked with, I'd be very happy to like exchange notes for how to do this. And okay, so while scaling and new features are exciting to talk about over the lifetime of a distributed system, vast majority of the cost would be actually operating it, right? And then all of this infra needs to operate at high scale with zero human toil, with extremely high reliability, right? This means that the system has to have no availability or performance loss despite constant ongoing disruptions. They're just a fact of life at this scale, right? There's OS upgrades happening, there's hardware upgrades happening, there's clusters expansion and contraction happening constantly. There's hardware failures happening across these thousands of machines. There's software deployments happening. And there's ongoing active load and stress tests and chaos tests disrupting the system. So disruption is just something like a fact of life at this scale. And similarly, while all of this chaos is happening in the system, we must have absolutely no data integrity issues, right? There's no, for planned operations that we can like foresee and execute ourselves in advance, there must be no user visible impact on latency and availability at all, right? And for unplanned operations, they must degrade gracefully, so very small blast radius, and must self-heal relatively quickly without operator involvement or human touch. These are pretty much table stakes for us, and that's a lot of the work to prove out such a system at scale to make sure it can meet these very strict criteria. So in this line, it's very small because there's a lot of other areas we are actively investigating. For operability, there's stuff like how do we safely upgrade and roll back minor and major versions for multi-petabyte clusters at scale, right? Like how do we do that safely? How do we operate efficiently with heterogeneous hardware SKUs in the cluster? At some point, it may not be practical to guarantee that all the 500 or 1,000 machines in the cluster have the same configuration. How do we guarantee stable performance while all of these operation maintenance is going on? Similarly, for a multi-tenant system, we need ideally per query type latency SLOs. It shouldn't be the case that a new user onboarded to the system and the previous user's query latency spiked up because of some conflicts or noisy neighbor issues. For our own operations, we need a way to accurately estimate cluster capacity so we can make onboarding and ramp decisions. We need query cost modeling, and we need quota enforcement mechanisms, both to protect the cluster and to protect users from each other. We are evaluating TiDB resource control feature at the time for these. And then, like as we exercise this system and put it through the paces in production, we've run into some resiliency issues that we fix as we discover. For example, we observe sometimes a persistent QPS queue across TiKVs that's not proactively balanced by PD. So we are working on figuring out how to address that. Sometimes stable heuristics are not updated after the bulk update I just mentioned in time, which causes large latency spikes until we run an analyze stable operation manually. We observed other issues like TiKV restart. Like when the TiKV node restarts, the query latency is a little high for a while until it catches up to the RAF log. And like a couple of other issues where a single TiKV node can cause cluster-wide latency impact. A lot of this, by the way, I didn't mention it in the beginning, but we are running TiDB version 7.1 in production, and that's what all of these experiments are based on. A lot of these have been fixed in newer versions or have features upcoming that would address this. So to summarize, as you can tell, we are very interested in running TiDB at scale at LinkedIn. And we're looking forward to the improvements that are coming up in the newer versions across all of these dimensions. And we hope to collaborate, learn from the community, and then contribute whatever we can back to the community. Thank you.